Sorry about that.
Well, thank you very much. I'm very honored to be here today. I'm going to be talking about how a public authority can become a first line of defense in a fraud, anti-fraud type of function. And this is me. I work at the machine learning lab at the Danish Business Authority. We're a part of the Ministry of Industry, Business and Financial Affairs. And the reason that we can be called a first line is that we also run the business registry. So we actually run the digital portal in which you, in a couple of minutes, fully online, can start a company in Denmark. So that brings us to a couple of problems, because we're tasked with diminishing the yearly VAT deficit by 1 billion kroner, which is not that much when you turn it into euro, but still a sizable amount. And this is a really hard problem, because we have a really short time frame to make this prediction. It's only a couple of minutes, and we have people standing at the door, so to speak, and they want to come in and start a company. What should we, how should we judge them? How should we evaluate the risk concerned with that? So we sort of formulated that the task is to understand business life cycles and the actors that have a causal effect on these life cycles. And luckily, we have something which is really important. We have access to other public data, so we can combine the business registry with information about annual reports delivered by these companies, some of the controls that other departments are making within the state, such as the tax department, and all the casework we have on hand in both our own and other authorities. So this creates a graph that's currently 150 million notes and about 200 million relations, and it tells us some really interesting stories that was previously very hard to see in the data. We have some cases of very unusual types that are not connected to fraud, but still have a number of relations that would be very hard to perceive by a human eye in a sort of tabular format. For instance, one person can have relations to more than 10,000 companies. If they are indeed wind turbines, a production unit, then you are related to that. So some of these complexes are really hard. And because we need to be able to react within a short time frame, and because we use machine learning, we also took some tactical design choices in that response time is obviously quite important, but explainability is also, because as a public authority, you don't want to play dice with business, with the business ability to survive. We don't want to dissolve companies that are safe and sound. And we also know that we're gonna hit and miss, so we need to be able to continuously improve this model and have adaptiveness in order to use data from other authorities. Now, as some of the other speakers have mentioned, the graph lends itself quite easily to combining different data sources, because all authorities, as they have different legislation, they tend to define their data objects differently. So a graph is a necessary step in the way of understanding data across different sectors. We also have the capability in-house. We chose to fund a machine learning lab. So I have about 10 colleagues from a wide range of backgrounds, ranging from fine art to astrophysics, and with a high degree of PhDs in the mix. because we needed to have this new capability of reacting timely, we built a machine learning data platform which revolves around these 4 factors. Firstly, we wish to understand life cycles and actors within companies. So the graph is a way to connect these data and also to encompass the need to understand time in the development of these relations among the actors and companies. And machine learning offers us some of the insights into data that's not easily understandable by humans due to the mass of data and some of the patterns within data based on math that's not readily available to us. And the explainability and continuous improvement creates the necessity for also having a strategy for adopting and using metadata, in that we actually have a second layer on the platform that is fed from our asynchronous event platform. The event architecture, the event-driven architecture, enables us to react whenever something is happening in our system, whenever someone applies to start a company. It also creates a lot of events that we've structured to portray the data sources, the models, the different data objects carry around, and they also convey some of the issues we wish to monitor concerning data ethics in general. So we try to parameterize some of the issues we wish to monitor concerning a model output. And as we have a full line of productization from the ingest of data to the case handling, all that is producing events. We can actually create some sanity checks from the model output to the case handling and sort of make the check if we're actually hitting what we're aiming for. You could say that data ethics is the measurement of an organization's guiding beliefs, and that makes it possible to react timely when that organization is doing something outside the realm of what is the ethic it's trying to follow. So these 4 things put together is what we believe enables us to do this. The tech stack, we started in 17, choosing Python, luckily. There was quite a bit of discussion about R. I'm really happy we chose Python. We went into the cloud to have the scalability and the orchestration by means of Kubernetes, and the containerization by means of Docker. And we chose Neo4j as the graph platform for building this knowledge graph, and then Kafka as our streaming data and message queuing platform. And then quite vital to the continuous improvement, also an evaluation plan for each model that involves our business units. So we have also a continuous evaluation of the model output in terms of falsifying or rectifying the model output in terms of the different various models we have in terms of classification by domain experts. So we can measure the metrics, but we can also get some input from the business units that this model is indeed still delivering value. And of course, we get a lot of marked up data from that process that we can then transfer into our training data. The metadata is quite useful here as well, as we need to continuously survey our system. We cannot use just an intention not to be evil. We need to really measure and make sure that we're not using data that it's not meant for that usage. And why that's especially important, I'll explain in just a second when I talk about our knowledge graph. lastly, we have a bit in our pipeline that we call the control tower, and that's actually the business unit's last defense about a model going berserk. We are dealing with probabilities, so it could happen that a model was falsely implemented or produced output of less quality. So they have the ability to mute the model and also to adjust some of the thresholds affecting their the system they are working in and handling the cases from. And I was actually surprised that also for the adaptation of these technologies in the organization, it's quite important from a cultural standpoint to have some sort of agency in the business units, that it's not, you probably won't mute the model, but it's nice to know that you can do it if necessary. So there's also sort of an acceptance of automation here at play. So the knowledge graph is conceptually comprised of three different data types. Firstly, we have the raw data from our registries. It could be annual reports, it could be some of the VAT numerical data, or some of the relations between various actors in relation to companies and the companies themselves. We then have a lot of just common metadata aggregations and the type of calculations you can make on top of data that's just objectively true in terms of delta values, and also as we have the luxury of actually looking between actors and what they do in relation to different authorities, we can also just look for discrepancies. For instance, if you write something in your annual report concerning VAT, we can go and check if that's also what you remembered to tell the tax department. And it sounds very simple, but apparently this hasn't been possible before because of the way a state is divided into different authorities. And then we have the last part, which I find especially interesting, and that's where we use machine learning models to to read and input different observations they make in data. So we actually also use the graph as a persistence layer to our machine learning model. And that's quite volatile, and that's why I'm emphasizing data governance here, because we are now in a situation where when something new happens in our data, we can sort of stand on the shoulder of our other observations and utilize another model to evaluate this new data event within the business structure. So this becomes quite important also from an ethical standpoint, because this model may have been meant for one usage, but we're suddenly reusing that output as input in another model. So we need to be able to trace the data usage in between and models. And over time, we expect that the growth in data will primarily be this machine-based data. And we expect to hit the 1 billion mark this year. We have another graph which runs on the telemetry data we have about the process of inputting data through our systems, and it's running around 500 million relations in a time series analysis. But that's information you can use both to investigate the type of information you can infer, the type of thing you look on something on your mobile, and suddenly on your PC you get an advertisement for that particular product. We can do that as well by looking among the telemetry data and discover some of the informal relations between the computational clients used to interact with our systems that can convey some groupings in the network that were not immediately present from the formalized data. So we've actually built a model that that utilizes this. So it's using output from some of our other models. A lot of our models are actually just working with producing data from a lot of the unstructured data we have, checking identity papers for consistency, and checking that some of the assets you deliver in your annual reports are actually complying with what they are supposed to be, and some of the what I call low-hanging fruit. There are a lot of auditors within business networks that audit the annual reports. They actually write in the annual reports for the company if there's something wrong. The problem is there's 270,000 annual reports, and there's a limited number of people actually controlling them. But suddenly, by use of machine learning, we can just control them all. So that gives us a lot of information back about these companies, and also it gives us some derivative information. Say we find a fictitious identity paper concerning an actor connected to a company, then the other actors connected to that company within that time frame suddenly becomes quite interesting, because you've been in the company board with a person that doesn't exist. That must have been a strange type of meeting. Now, this model we've built combines 224 parameters, and this is highly complex, and it's immediately perceivable why this isn't readily transferable to the human mind. And the way the model works is that it looks on the company on an individual basis and explores the context of that company. And within that context, there's 224 parameters. There's also the aspect of time. So the time of that company's life cycle is also a factor to the strength of the statement those parameters make. So we're really coming close to sort of a context problem. What's the context of the problem we're trying to solve? And it seems like we're getting there. Of these 224 parameters, most of them are actually some of these metadata, the processed aggregated parameters. The next line are the raw data, but moving in fast are all these machine learning driven insights. And we'll be looking into an actual example of how this model performs. This is a company that a few years back, we have the luxury to look back in time and try the model. And when it's formed, there's a risk score of only 11%. One of the, and I have made down here, P is person, V is company. Then we have the business classification and the type of business and the address. So, and the current state of the company. So the company is currently alive. It's just born, you might say. And there's nothing really curious about it. It's only 11%. Two directors within this company, and none of them are looking suspicious in any way. Then we move to 6 months, and suddenly the model reacts. We have a new person attached to the company, and we have a new address. And both of these two new nodes in the network, the models looks into their background and is immediately concerned. So after 6 months, you would have the basis of perhaps taking an interview with this company and looking into their method of operation. A month passes, there's a change of address, and the model is now responding with a 64% risk of fraud. And if we move ahead of time, there's a new person involved, a new address, but nothing that really changes the score in the 11th month. But then in month 12, it becomes very agitated, our little model, because the company also has a dual change of the company classification, and the company classification is, as a method, is a taxonomy for what the company deals with. So you have a classification for dealing with bananas and one for bicycles and all that. And if you change that, it becomes interesting to the model. And actually, in the month 17, this company was surveyed by the authorities and found to have a VAT fraud of close to 4 million. And I didn't cherry pick this example at all, of course. Now, the principles we adopted are, of course, the almost unfair advantage of having access to data from other authorities, but also applying an event-driven architecture, so we get both a metadata layer of what happened, so we have a single source of truth in terms of what is the business network, but we also have an additional single source of truth of everything we've ever done to data by means of this derived layer based on these events. And this graph adaptation has helped us a lot to contextualize these business life cycles and also combine graph with machine learning, because the individual model is sort of an autistic way of engaging with life. It understands a fraction of reality very well, but it's not really adept at understanding how the world is connected. Luckily, the graph is. And by using the graph as a persistence layer and as an in-output, as a basis for these models, we hope to achieve also that our models come to share the same view of the world. So we will also have an easier way to govern all these different models. So the chatbot will base its information on the same data as we will do our case handling with, so we don't say one thing to our clients and judge them by another standard. But also, it's more sort of a capitalist view on data, that you can actually create more growth in data by combining it. So this machine learning is helping us use all this data for good, and also monitor and trace this usage so we can explain. And as we've built in this evaluation process, our business units are also heavily engaged in monitoring that the models hit what we aim for and that they deliver business value. So all in all, the usage of graph and ML with the event layer enables us to control all the companies in real time. It enables us to do so continuously. So every time there's a change in the data, some model starts doing something, and when it's done, it creates an event and another model continues. So we can break down some of the complex problems into less complex models, and that helps us with keeping our models explainable. And you can say the entire ecosystems then becomes a highly complex machine, but with the benefits of full transparency and traceability. So.
Any questions for Marius? Yeah.
Yeah.
When did you start all this?
So the question was, when did we start? We were given the task in 2018 to do this, but we actually started in 2017, getting into graph. I had previously done some work on a database on species, all living things, in 2015. And I thought, well, this is going to be swell, because you have the register actor, the people discovering a species, they have to get their name and all that, and you have the and the benefit of when that was. So, this is a great relational database. Finally, you can do the bitemporal thing because we discovered this species, but the species existed in another space and time. But then I became aware of DNA testing. So they change where species come from all the time. And that became a relational nightmare. So I became interested in graph because some of these time series and relations are more easily to model in that sense. So 17 we started cloud, 18 we came into production with the graph. Yes?
Yeah.
Yeah, yeah.
Do you use any kind of like RTF schema or ontology to capture the metadata?
Yeah. We were, the question is if we use RDF or ontologies to capture the metadata. Well, actually in 17 we did analysis also of the terms that runs through the telemetry data. So the hidden agenda with the metadata layer of everything that happened, I really love that data set. I mean, a single source of truth of everything that happened. It's a dream come true, and it's certainly the intention that we will use that metadata also to develop the graph and the ontology surrounding this area of this field of interest. So yes, we're moving in that direction. And I was hoping that we could use maybe shape-constrained language or something like that also to govern our data. But I'll maybe be talking to Emil later about how could you do that with GQL and Cypher.
Can you give some examples of which machine learning models you use and what the pipeline is like?
Yeah. If I could give some examples of the machine learning models we use and some of the pipelines. Sorry?
Can you repeat the question?
Yeah, I was asked if I could give some examples of the machine learning models we use and the pipelines. A lot of the models we built are mainly NLP models because we have a large amount of unstructured data. So it's mostly scikit-learn stuff. We have added a fifth layer to our four-layered production cycle from, the usual develop, test, pre-prod, and production environment with a lab environment where we sort of run ahead and try a lot of these hypotheses and do the data transformations. So we have an early indication whether that particular model and the data are viable to engage in a production lifecycle. The model we've built in terms of the anti-fraud is a gradient boosting model using XGBoost, actually. But we also built some models using TensorFlow, for instance. We have a model that checks. Some of these processes you still have to deliver paper with your signature, otherwise it's not you're not compliant. So we have to use a machine learning algorithm to check whether there's a signature on this piece of paper or not in the attached file. So some of the applications are kind of stupid, but it's still the law that there has to be a signature, so we check for it.